Today we're going to be covering the basics of intermolecular forces. These intermolecular forces are commonly referred to as IMS. And this is an important video to understand regarding biology because these electrostatic IMS are the reason for many reactions, the solubility of molecules, and it is occurring everywhere within our bodies and around us. Now, IMS are electrostatic interactions that occur between molecules. This can be remembered from the prefix inter and intermolecular, as inter means between two groups. There are three types of IMS. On this slide is an overview of each of these interactions. There are London dispersion forces, LDS. This interaction can occur in all molecules except ions. LDS occur from a fluctuation in dipoles and the dispersion of partial charges. There are factors that change the strength of these LDS, which we will get to later, but the size of the atom, the surface area, and the shape all affect LDS strength. They are the only and strongest interaction that nonpolar molecules can form. The next IMF are dipole-dipole interactions. These are present between molecules that are permanently polar. A molecule is permanently polar when there is one atom within the molecule that is more electronegative than the rest of the atoms. So because this atom is more electronegative, it is going to be drawing the electrons, making that atom partially negative and the rest of the molecule partially positive. The dipole-dipole interactions are generally stronger than LDS. The last type of IMF are hydrogen bonds. Now this name is deceiving because hydrogen bonds are not bonds, but just interactions between molecules. And there are quite a few requirements that these two molecules must have to be able to hydrogen bond. Briefly, a hydrogen bond is between two molecules. One molecule must have an oxygen or a nitrogen or a fluorine covalently bonded to a hydrogen. In the second molecule, there must be an oxygen or a nitrogen or a fluorine with lone pairs. We will discuss more in detail later, but hydrogen bonds are the strongest IMF, and this is because of such a big polarization between the hydrogens and the oxygen, nitrogen, or fluorine, that it causes such strong partial charges. So let's talk about London dispersion forces. London dispersion forces occurred during the fluctuation of electrons within molecules. These molecules are always in motion, and so with collisions, a molecule can develop a temporary or instantaneous dipole. In this diagram, we have two molecules of methane. Methane is a nonpolar molecule, and in the first step, there's just two molecules of methane that aren't interacting because there's no polarization. In the second step, methane A, in the second step, methane A develops an instantaneous dipole due to the unsymmetrical distribution of electrons. So there are more electrons over here, making this side a partial negative, and then making this side a partial positive. In the third step, you see methane B induces into a dipole because of methane A. So now they're interacting. Methane A's partially positive charge is going to draw methane B's electrons, and this will cause partial charges in methane B, forming an induced dipole. Now these two are not interacting, these two are now interacting due to the partial charges. Now these LDS strengths can be affected by some characteristics, like we said earlier. If two atoms are larger, they will form stronger interactions. And if there's more surface area, then they will form stronger interactions. If there's more, and the shape of the LDF makes it easier or more challenging to form LDS. It just depends. LDS are very so much like humans and germs. Specifically, if someone who has a cold and coughs on someone healthy, that healthy person can become sick. those germs are infecting or inducing a healthy or non-polarized molecule to becoming a dipole or a sec. Dipole-dipole interactions are much more simple to understand. Dipole-dipole interactions occur between two permanent dipole molecules. The polarization in the molecule due to the electronegativity gives permanent positive and negative charges to the atom. This attracts the opposite charge to interact with another molecule. So here is an example of the molecule ammonia. The arrow shows the directionality of the dipole. The way the arrow is pointing is where the electrons are mainly located. So you can see that more electrons are here, making this negative, and these partially positive. Now the arrow at the bottom of ammonia molecule is going to interact with the arrow in the molecule at the top. Now these dipole-dipole interactions are stronger than LDFs and can interact with molecules to form LDFs with other molecules, even if they are participating in dipole-dipole interactions with another molecule. So these molecules can make LDF interactions as well as dipole-dipole interactions. Now to simplify dipole-dipole interactions, they are very similar to a magnet. The magnet has a positive and a negative charge, and it is attracted to the opposite charge, similar to how the polar molecules interact. Now, hydrogen bonding can be difficult to understand, but is very simple to identify once you understand the requirements. Now, again, hydrogen bonding is just an interaction. It is not a bond. It is the strongest IMF out of the three, and that is because hydrogen bonding can occur within electronegative atoms that are very electronegative, so they will cause a larger difference in polarization, giving greater partial charges. Now, hydrogen bonding works is hydrogen need to be bonded to an oxygen, nitrogen, or fluorine. And as you can see, water in the upper left corner, you can see that hydrogen is interacting. Sorry, this mouse keeps going away. Hydrogen is interacting with an oxygen, nitrogen, or fluorine, in this case, with lone pairs. In this case, it's an oxygen. So you can see that water in the center is interacting with the upper left corner, hydrogen, which fits all the requirements to form a hydrogen bond. Now, water is the most common example of hydrogen bonding, but I wanted to show you another example. So if you look at the bottom left, you can see that water is hydrogen bonding with an ammonia because this is a nitrogen with lone pairs. A hydrogen bonding to a hydrogen that is attached to an oxygen, nitrogen, or fluorine, in this case, oxygen. If two molecules hydrogen bond, that means that they can also form dipole-dipole interactions and LDFs. They can do all three. Now, solutes can hydrogen bond with a solvent to dissolve water, or to dissolve, I'm sorry. Hydrogen bonding is how solubility occurs within molecules. It occurs all around us. For example, in DNA, there are two strands that are wound together. So this is one strand, and this is the other. And they are wound together, and these strands are connected together through hydrogen bonding. Now, this is just a glimpse into the three IMFs. They are very important to biology because it allows molecules to interact with one another. Proteins can fold specifically because of all these IMFs. Your DNA strands specifically can stay structurally intact and are in charge of many more things. I hope this helps. Thank you.